What are some of these tests? So once we have established that the terms do go to zero, that sum, the infinite sum, has a possibility of converging. So our test that we're going to use is we're going to use a harmonic series as a key to one of our tests. And it's really just as a comparison. So just to make sure we're clear, the harmonic series does not converge. Okay, it's divergent. It has an infinite sum. However, some of these p series, so these p series are when we have the harmonic series with a power p on it. Some of them converge, have a finite sum, and this happens when p is greater than 1, and sometimes they diverge, and this is when p is less than or equal to 1, and equal to 1 being the harmonic series. So the harmonic series becomes the relative boundary. It's our boundary series for convergence and divergence. So we need to establish some guidelines as to when the infinite series converges and diverges. So one of our informal tests is going to be this just comparison. And one of the comparisons we can make is to the harmonic series. Now, it's important to understand that although this is an informal test, it's a valid test. Okay? If we can establish that it converges based on an informal comparison, then it's a valid test and we're going to say that it converges. This is what we want. This is what we need. We're going to be able to use this for our purposes. So the comparison is going to be to the harmonic series 1 over n. So if I have something like this, so we want to establish whether the series converges or diverges, we can see that we have a 1 over root n. Does that series converge or diverge? Well, we're going to do this with a comparison to 1 over n. And to kind of model 1 over n, and note we're going to use this 1 over x function. So this is y equals 1 over x I've drawn here and here. And we're going to use this as a basis comparison. And we've looked at this before as an integral, and the area under this integral from 1 to infinity is infinite. And if the function behaves in that way, we can kind of think that the series behaves in that way as well. So this as a series would look like this. We would just take the middle value of 1 and we'd have an area of 1. We'd have an area of 1/2. Oops, I just didn't draw this quite correctly, but I would go from 1/2 to 1.5 and draw a bar, and there's an area of 1. This here would be an area of 1/2, and the area under that curve is similar to the sum of that series, which is the bars. Now, if we were going to compare this to 1 over n, I'm going to draw this in a different color. So this 1 over n, I can establish whether this 1 over n converges or diverges when I look at the graph of this 1 over n. So this is going to be, 1 over root n is going to be a graph that kind of goes like that. And the sum of those is going to be a bunch of rectangles I can draw into there. And I know that the area or the sum of those rectangles is going to be, the red rectangles is infinite. Well, if that's the case, I know that the 1 over root n, the sum must be bigger because there's more space underneath that curve. And therefore, it should be, if the 1 over n is infinite, the 1 over root n must be infinite. So I'm going to then conclude by comparison to 1 over n that it must be infinite because we know that this sum is greater than the 1 over n function, which I know is to be infinite. Okay, so if it's bigger than infinity, it must be infinity. So that is our comparison. We're just comparing that to 1 over n. And we could do a similar comparison when we have 1 over 4 root, the fifth power fourth root of n. And if we were to sketch this diagram and compare this to the 1 over n function, okay, which I'll do in green, it's going to look a little bit different. It's going to kind of follow the same thing, but then because the power is bigger than 1, it's going to come down to 0 a little bit quicker. So if I compare that to the area under the 1 over x function, okay, and although I'm talking about 1 over x, we're going to make the leap to that. What happens to 1 over x is going to be similar to what happens to 1 over n. Not the same, but similar. And the same can be said about this function here. So that function I've drawn in green would be y equals 1 over x to the power 5 over 4. If that power is bigger than 1, we're going to pinch down to 0 quicker, which is then going to be a finite sum. And the only reason we can say that is because 1 over n, although it's finite, we can't say that less than infinity is finite. 1 over n is special in that because it's a boundary series, if it goes down faster than 1 over n, we will say that at that point, those are finite sums. So we're going to say that this is equal to a finite sum because this is less than our boundary function of 1 over n. Okay, now the argument can't be to infinity because less than infinity can still be infinity, but less than 1 over n as an infinite sum will be finite. So we can then generalize these p-series in that any p-series greater than 1, so when p is greater than 1, or sorry, less than 1, this is diverging, or an infinite sum. If it's equal to 1, it's still diverging because this is our boundary. This is our 1 over x function, or 1 over n function. This is diverging. And because this is our boundary function, once we get past that function, where p is greater than 1, we now can say that this is converging. And this is a standard that we're going to establish. And this is a very useful standard then when we see any of these p-series.